Okay, so apologies for the confusion and the delay, but we're glad to present Mustafa Mukadam today. He's a research scientist at FAIR, and before that, he got his PhD from Georgia Tech. He worked with Byron Booth for his PhD, and he did a lot of cool work during his PhD. And currently, he's working on leveraging priors that we all know to design better learning techniques for robots, particularly in motion planning. He's also won uh, Best Paper Awards, I think at IGRR. Just correct me if I'm wrong, but yeah, really looking forward to your talk. Over to you, Mustafa.
Yeah, thank you for the nice introduction and excuse me. Thank you for the invitation as well. Uh, yeah, I think in these virtual times, we have other technical issues besides the usual projector malfunction, but I'm glad we got started. So today I'm mostly going to be focusing on motion planning from the trajectory optimization perspective. And largely the story is going to be a journey through how we can, like you said, leverage the priors we know and love, but also mix in the sort of the power of modern deep learning and machine learning. So it used to be this debate many years ago, I guess a few years ago, in this binary choice of whether we go with priors or whether we go with deep learning. And just to elaborate this point a bit from the motion planning perspective, there were all these nice traditional search sampling optimization methods that you could inject prior knowledge constraints into. They were highly interpretable, but they had their drawbacks. They couldn't leverage past experience. They would essentially be brittle outside of the domain you were trying, and in some sense introduce model bias as well. And more recently, with the advent of deep learning, we started seeing some excellent methods that showed a lot of promise in terms of going from pixels all the way down to actions. They were highly data driven, very flexible to design, but you started seeing other drawbacks like losing interpretability, difficulty in incorporating known constraints, and trying to learn things that maybe weren't necessarily needed to be learned. And these sort of challenges were especially more prominent when it came to doing machine learning for robotics, because getting data is much harder, and getting things to work in real systems is its own challenge. So uh, clearly the conversation has shifted now, where it's no longer this binary choice. We've realized that there's actually a spectrum here, and we can try to operate somewhere in the middle so that we can take advantage of both ends of these. So we've started seeing methods, particularly in sampling based motion planning, and a little bit in search as well, in terms of using machine learning, deep learning techniques like these to sort of start converging on the middle ground. In some sense, the choice is no longer whether to go with priors or whether to go with learned models, but actually the question is, the more interesting question now is, how do we get this best of both worlds, and how do we essentially live in the middle of this spectrum? So that's kind of what this overarching exploration is going to be in this talk, specifically in the context of motion planning and trajectory optimization. So how do we leverage both ends of this spectrum? So I'll start talking about a paradigm of motion planning as an inference problem, and I'll show how do we design these using factor graphs, and then later we'll talk about specifically how we can actually leverage this underlying factor graph structure to accomplish learning, and be at the middle of that spectrum we just talked about, where we start getting benefits of both sides of the world. So let's start with first building the foundation. So we'll basically go with first principles and arrive at the reasoning behind why would we want to uh, let's say plan using an inference based strategy. So in typical problem you would have some start, some goal, and let's say this is relatively simple. you have no environment, no obstacles, nothing. So all you got to do is just go from this start to goal. Now you can have many different trajectories that can take you to the goal. And if you're trying to minimize some objective, let's say shortest path or smoothest path or something, you could have a straight line connecting start and goal. But essentially, all these options could be nicely summarized in a single distribution, uh, where theta would be here the trajectory with some mean and covariance that describes this distribution. So we'll just call this prior. And intuitively, what you can think of this prior as is trying to give you a trajectory that is as close to the mean as possible, which is what this function here would be defining. And so you're saying that what would be some trajectory in this distribution that's as close to the mean as possible, and then this mean can try to capture some notion of optimality, typically smoothness in the trajectory. And so if we start adding back in the stuff we were ignoring, things like what typical planning problems would have to do, collision avoidance or other constraints and objectives, uh, what we could try to do is capture those objectives in a likelihood function. And essentially then the planning problem just becomes trying to find this posterior, where the dotted red line is sort of the mode of this posterior distribution, which lends itself nicely to a maximum a posteriori inference problem. So that's kind of the high level idea for uh, designing motion planning as like an inference problem. Uh, Obviously, this in a more general sense can be very expensive to solve. And so here what we try to do is employ probabilistic graphical models and sparsification techniques there to make this problem much more efficient to solve in practice. So one trick is this is where factor graphs would come in, where the trajectory would be defined by these chain of states, and then these red things are connecting adjacent states into a chain-like trajectory. And so the product of these red factors essentially gives you back this original prior distribution. But because this covariance has a inverse which is really sparse, you essentially get this chain-like structure out from that distribution. So let's say if you were to use some more commonly used kernels for this Gaussian process, uh, like an RBF kernel or something, you would get a graph structure that essentially had one red node that was connecting to all your states. So this K inverse would then be really, really dense. And the reason this becomes important is the inference problem we're trying to solve at the top here is much more efficient to solve when you have this nice sparse structure. And it's a reasonable assumption because most trajectories, if you're considering position and velocity, can be Markovian in structure. So this chain-like thing is quite typical. So that's kind of what prior looks like. It's trying to, let's say, find smooth trajectories, and then we can have this likelihood function that's trying to capture everything else about the problem, reaching a goal, avoiding a bunch of obstacles, things like that. And then this edge function can be sort of based on the problem you're trying to deal with. So it could, like we said, capture some notion of obstacle avoidance, but it could also be other cost functions trying to avoid joint limits if it's a manipulator. It could be end effector motion constraints, the robot holding a cup and needs to be horizontal because it doesn't want to spill something in the cup. So those kind of things could be captured by this likelihood function here and thrown as factors in this graph. So we did all this groundwork and uh, put in all this machinery to construct this inference problem. And the reason it becomes really efficient to solve is we can leverage this duality between inference and optimization. So the simple idea is just take the negative log on that first equation, and what we get out is the dual optimization problem, which is just a nonlinear least squares problem. So the mean or the mode of the posterior distribution here is just the optimal trajectory in this minimization problem here. And this trick is actually not new. It's commonly explored a lot in SLAM problems, which also pretty much use factor graphs to design large nonlinear least squares problems. You might have heard of things like postgraph SLAM, things like that. And essentially, that's kind of the machinery we just directly leverage here, where we design the motion planning problem as an inference problem on factor graphs, and then just actually directly use libraries that were originally designed to solve SLAM problems, and then just throw our planning problem at it. And that gives us solutions really, really quickly and really fast, because SLAM community has tried to make these solvers fast and efficient over the last couple of decades. So we just get all of that for free. In fact, we can take that connection between SLAM planning a little further and actually use incremental inference techniques like ISAM that allow you to re-optimize factor graphs more efficiently if only a small amount of information has changed. So in SLAM, this is typically quite common when you're doing the robots moving and you get some new sensor measurement at a new time step. Typically you just have one new factor to add to the graph that's giving you the latest sensor measurement. So the graph hasn't really changed a lot, and it doesn't make sense to throw away all the computation that was done before and start optimizing the whole trajectory from scratch. And these incremental inference techniques, bring down the optimization from order of milliseconds down to microseconds. So it's like a 3 order of magnitude speed up over there. So we use again that same machinery here, where we can solve replanning problems uh, in a similar light. So if your robot is moving and it's trying to get to a certain goal, and all of a sudden the problem definition changes and the goal has slightly shifted to somewhere else, all that would change is this factor here, but the rest of the graph is same. So you could essentially just do incremental inference and resolve the planning problem online really, really quickly. And we're talking about microseconds here. So replanning in real world, real time constraints becomes much more doable with these kind of approaches. So we released the code on GitHub. It's out there. We did a bunch of benchmarks in this IGR paper as well, where we compared our method with a bunch of different trajectory optimization that are state of the art, and also sampling based algorithms. And in these extensive benchmarks, what we found was optimization methods are quite well suited for the problems we were looking at, specifically large degree of freedom robots that don't necessarily have to navigate a lot of tight constraints like maze or corridors, which sampling based methods excel at a lot, but become very slow when you're trying to deal with these high dimensional problems. And in particular, if you look at the max computation time for our method as well, it's still much less worse compared to the worst case time complexity for other trajectory optimization methods as well. uh, so yeah, basically we were able to lay a solid foundation using these inference style factor graph based motion planning. um, and we
Can I ask-
realized that.
Sorry, can
Yeah.
I ask a question?
Uh-huh.
So I wonder if you could be a little more precise about, like, in this example, what those like obstacle prior factors look like. And do you need, like, if you have M obstacles, do you need M obstacle priors attached to every single state?
Yeah, good question. So just getting into the details a bit about the obstacle factor, the way it works is the cost function that's defining the factor is like a hinge loss function that operates over the sign distance field of the environment. So you, from perception, you get to some sign distance field, and then at the optimization level, your robot's approximated with a collection of spheres. And what you do is you apply forward kinematics to find where your spheres on the robot will be in the workspace, and then check for each of that sphere what is the closest distance to the environment, and then use that distance in a hinge loss style cost function. So if you're a certain safety distance away, then the cost is 0. If you're, further closer to the obstacle or penetrating the obstacle, then the cost is larger. And then all of that gets projected back into the cost and the gradient to move the trajectory out of collision.
Okay, I think I get it.
Mm-hmm. I skipped over a bit of detail, but since we're using this continuous formulation through GPs to represent the trajectory, you actually don't need to have a very fine discretization that's common for trajectory optimization. You can get away with a few sparse set of states, but then the problem is, how do you ensure path safety? So for that, what we do is we have these binary collision factors that connect between two states, and during optimization, they just interpolate using the GP regression to figure out what the state is in between two states, and then check the collision cost there, and then project it back to the state, so that only the sparse set of states are being optimized iteration to iteration. So that gives a significant boost in speed as well in terms of performance. All right, so before we sort of get into the magic of learning, I wanted to maybe spend one more slide just kind of delving into this flexibility that factor graphs provide us in solving these kinds of problems. So we took this a little further. We talked a little bit about the connection between planning and SLAM, since they're essentially formulated using the same mathematical tools and underlying software. What we did in this work was actually to connect those two in the same optimization process. So if your robot somewhere along the trajectory, whatever is in the past automatically becomes a solution to an estimation problem, and whatever is in the future automatically becomes a solution to the planning problem. So estimation and planning are almost just kind of solved jointly, and both communicate with each other. We had some other follow-up works in how to do sort of receding horizon NPC style control in dynamic environments, and Zen was actually involved in this work as well, where we took like a whole network of trajectories, because factor graphs allow you to initialize things like those, throw it on some environments, and then get it to solve harder maze-like problems that trajectory optimization usually struggles with. We also extended that to sort of online settings as well, where you can see this red trajectory jump over obstacles and essentially allow you to dynamically switch between homotopy classes in an online setting. So the summary is basically that these factor graphs provide us like a nice data structure, which is quite flexible in doing a lot of different things. And in particular, we'll sort of explore how learning becomes much easier if we think in terms of these data structures, factor graph-based data structures, and we'll see kind of how can we do learning in a way that is adding value over traditional methods, rather than doing learning just kind of for the sake of learning. In this work, I'll use this drawer opening thing as an example for motivating how we can sort of leverage this machinery to do learning. This sort of trajectory that the robot is trying to go get to the drawer and open it, it's in the machinery we just talked about. It's going to be hard to formulate how to achieve that robot motion, because there's constraints involved now. And so it's kind of hard to hand design that cost function that we were trying to optimize. It's no longer just being a smooth trajectory that avoids obstacles. There's this constraint of getting to the drawer and opening it. So this sort of lends itself nicely to can we learn this? And the sort of short answer is actually looking at a distribution of what possible trajectories could look like. So if you imagine the robot having a number of different ways, if there were no obstacles and it was like a open environment, it was just the robot and the drawer, it would be a bunch of different trajectories that get to the drawer, and then the options become really limited, where there's only a certain way, because you have to respect the kinematics of the drawer in opening it. There's a very limited way in which the robot can move after that. So if you sort of following my train of thought, this is essentially what we can think of as a prior in our framework, inference framework here. So the idea in this work essentially was that we just learn these GPs from a few set of demonstrations in open environments. So there's no obstacles. It's just completely collision free. And all we're interested in seeing or learning is how should the robot move so that it can accomplish this drawer opening task. And then what we can do is, this priors obviously define this red factors that we're trying to learn from the demonstration. And then there we get this distribution where, these red trajectories are now the demonstrations, and that's approximated by the blue line in the middle, which is the mean of that distribution, which we just learned. So what we can do is now use that ordered machinery from the planning problem and inject our likelihood to be any new environment that we want to generalize this learned model into, and then apply inference and then reproduce that same motion, but with different constraints. And so this sort of helps really well with generalization a lot, because now we're not concerned about learning in every possible environments and getting a lot of data in different settings so that generalization is easy. Now we just need to get at the core of what is the motion for the robot and the task, and then plug in this modular way of integrating likelihoods, and then generalize it to any new environment that it might not have ever seen before. And so it's kind of like a flexible way of learning some components in the graph, like these red factors, and then plugging everything else that's maybe hand designed, and then just kind of consolidating all of that through this optimization process. So here's a few examples where the robot is trying to accomplish the same task under different initial conditions and obstacles that were not present during the learning phase. And it's able to generalize it. The caveat or the limitation is, of course, that you have to learn these like skills or prior models for every new task that you might have to do. But the question now, it really is, this is more sort of a traditional way of learning things where you get demonstrations and you do linear regression or something, learn this GP. Can we actually leverage deep learning in some way that we don't require hand demonstrations? We could learn from high dimensional inputs like videos or images and things like that. And the I guess the one way it's quite common is you have these high dimensional inputs and then you learn some perceptual features, and they're maybe supervised with some loss. The disconnect usually comes with the perception being separate from the planning phase. And so perception is trained really well to do the task it is doing. And then the idea is that you just plug it in with a planner and then let it do some task. And the downside with that is sometimes that the perception is not aware of the last task loss that the planner is doing, and the performance of this overall system is really coming just from what actions the planner is going to take. So the question really is, can we still pre-train all these perception models like we were doing before, but then have a differentiable planner that can still allow us to backpropagate task losses back to these perception features that we had learned or pre-trained before, and then fine-tune them on the real task loss that we care about. So that's kind of what I'll talk about next. So if you look at this nonlinear least squares objective that we had before, this covariance for, let's say, the obstacle objective, this was something that we were hand designing, and essentially in practice it was just a scalar multiplied by some identity matrix, and you can think of it as like a weighting function that's trading off how much you want to be smooth versus how much you want to avoid collision. And typically for optimization, this can lead to weird local minimas where, if you haven't gotten this balance between those two pieces of the cost function right, then you might end up in weird local minimas that are not collision free. And, and I guess if you're doing this by hand, it's only humanly possible to maybe vary a few scalar numbers. So there's no way we can design this covariance matrix by hand such that it's not only varying across state, across the whole trajectory, but also across time. So it's far less expressive. You're essentially relying on one scalar number to trade off a whole set of different problems. And so in practice, what this results in, despite the good performance, is, let's say you pick one particular setting and have two different environments, you can easily succeed in one, but completely fail in the other, just because of the fact that you've picked this certain value that doesn't lend itself to these kinds of sparser environments. And if you, let's say, tune it again and try it, maybe you start solving the problems you were failing, but then you fail on the other problems. And the question really is, how do we set this up so that we can solve a large set of problems? And this is kind of the example I'll use to motivate the use for where this end-to-end differentiable planner can be helpful. So we have this objective from our planning problem, and we want to see how to make this actually differentiable. So this is solving a nonlinear least squares problem. And
can I ask you just a really quick question? I don't know how you're supposed to do questions though, but so I'm just a little confused as when we have such a formulation with a mean, you always have to start from roughly the same place, right? Or otherwise, you're just right off from the start. Does that make sense?
So are you talking about initializing the optimization?
No. So like for the probability of being away from your starting point of your mean is super low. So like if you can only learn when you start from the same point and go to the same point. Is that correct, or am I misunderstanding something?
Oh, are you talking about the drawer opening example?
For example, yeah.
So you're saying that the robot needs to start in a location that's close enough to the mean of the distribution?
To mu zero, right?
Uh-huh.
Is that correct?
There's some flexibility in that. So this K here is trying to capture what is the spread of trajectories that the robot can possibly handle. So you're not restricted to a single value where you have to start the robot there, otherwise nothing works.
Okay, sure. I mean, yeah, okay.
So the start state can also be a sort of a Gaussian distribution, let's say.
Because the thing is, like, if you're in a cluttered environment, then your Gaussian assumption will say that you can start from, and you want to start from many places, then your assumption will be that you can like continuously start everywhere, whereas it might not be true. I'm just trying to like wrap my head around this formulation. Is that correct? Are there fundamental problems to starting far away from your mean?
Not really. The mean just depends on. So you can think of the mu zero as some known start state or some known measurement. So you could be wherever in the workspace relative to the environment, and you're essentially getting like a measurement mu zero for where the initial conditions are. And if you're really confident, then the covariance with respect to mu zero will just be super small. Otherwise, it can be slightly bigger. And it'll just constrain the rest of the GP to sort of get hooked at that location. Does that make sense?
Yeah, it makes sense. I would need to do more GPs, and this is not the right place to like have an extended conversation about it, so.
Okay. All right. So we were talking about this problem of hand tuning these covariances and sort of using that as a example for motivating where differentiable optimization could be really useful. So if you can imagine, a scenario where you're given some environment image and you have some learning method, let's say your favorite neural network, it can process that image and then predict some covariances that this optimizer can then use. And then the resulting trajectory can be checked against, let's say, some expert. And then that gives you that nice supervision for tweaking the parameters of the network that's being learned. And so that serves as a good sort of example for seeing how this sort of end-to-end differentiability within the planner can be used to at least address this specific problem. In the more general setting, you're not really restricted to, if the whole pipeline is fully differentiable, you can essentially have any piece of this objective really be just kind of parameterized by neural networks. So you could learn, let's say, your cost function here or some covariance here. So in the previous case where we were trying to learn these from human demonstrations, they could be some neural networks that are learned from other data that you might have. And so the core idea is really just that, we can pick and choose what we want to learn and what we want to hand parameterize, and then train everything end to end based on some task laws that we actually care about in terms of achieving. So let's just see how we can, turn this optimization problem into a computation graph so that we can differentiate through it. So if we sort of unroll this nonlinear iterative scheme and just look at one iteration, you have your environment, you have some initial or current trajectory that you're trying to iterate over, and then you have some fixed set of parameters. They're going into this factor graph objective, your nonlinear least squares problem statement. And the way you typically solve nonlinear least squares through Levenberg-Marquardt or Gauss-Newton or something, what you try to do is around your current trajectory, theta I, you would try to linearize this nonlinear objective and then have some linear system which is trying to solve what is that delta update that you need to make to your trajectory so that it gets closer to minimizing the objective. And so you can solve this linear system, find out what this update will be, and then essentially get the updated trajectory out in the next step. And to just complete the nonlinear loop, you can check for convergence. If the trajectory is not changing, then you're done. If it's not quite converged, then you go back and now that's your new trajectory, and then you do this thing over again. So far, what we've just really seen is how GPMP2 was using nonlinear least squares to just optimize for a trajectory, and we just wrote it out again as a computation graph. And because all these operations are mostly matrix operations, this whole graph is just fully differentiable, so you can backprop through that. So now that we have this, what we can do is use the environment and let's say maybe even the current trajectory to set up this module here, W, that can be whatever neural network or some kind of feed-forward network that you're trying to use to predict some parameters that are learnable now that define your nonlinear objective or missing factors in your graph. And this sort of just now is like a flexible way of choosing what you want to hand specify and then choosing what you want to learn and then feeding it into this differentiable optimization scheme, and then just using a loss at the end that could be something like a imitation loss or a reinforcement learning loss, so that you can backprop through the whole unroll step of the optimization and then update these learnable parameters that you're interested in. So in the specific example we were talking about with just kind of tuning the obstacle avoidance weight functions, what you could do is use the image and the sign distance field for the environment, just kind of simple convolution feed forward networks. And then this learnable phi here would just be the covariance that we're interested in trying to estimate. And then the imitation loss that we ended up using was just kind of RT star, which gives us, globally optimal. It serves as a nice expert because it's giving us globally optimal solutions, even though it's going to be slow in practice, it gives us nice supervision for training these. And then at inference time, our optimization scheme can be really fast because it doesn't need to do sampling-based style of planning. So going back to our example where we're using this scalar value to just basically trade off between optimization and keeping the trajectory smooth or keeping it collision free, and then we saw it would succeed in some environments and fail in the others. Now we can use this differentiable optimization scheme so that we can actually learn this covariance, and not only learn the covariance in sort of this original scalar way that we were using before, but now since it's a neural network that's predicting this covariance, it can just be arbitrarily large. So you could imagine this covariance predicting a different value for every state in your trajectory, and also not only something that's changing over time across the trajectory, but also changing iteration to iteration in the nonlinear least squares optimization as well. So essentially you now have a way to predict all of these weights in your optimization that are much more expressive and flexible, which there's no way to just kind of design by hand because there's just too many numbers to tune. And so, this covariance is now actually a function of the trajectory and the environment. And then, at least in the examples that are in distribution, you can start predicting all these covariances at inference time and solve problems arbitrarily complex as long as they're in sort of the vicinity of the distributions you're trained on. So this is kind of really just kind of early stages of showing where differentiable planning can be quite useful. I think we're barely scratching the surface. The sky is really the limit here. As long as we're kind of using this factor graph backbone to design our optimization problem, you can just kind of pick and choose what you want to learn and what you want to hand design. And as long as everything's differentiable, you can learn the things, even pre-train them and then fine-tune them on some end-to-end task loss. So this going forward, I think this can be like quite a powerful way of using differentiable optimizers and motion planning, and actually seamlessly connecting it to perception networks, and essentially just kind of training across systems rather than training across like individual modules. So yeah, I guess I already kind of summarized. We looked at how planning as inference can be done with factor graphs, and then why this sort of factor graph backbone is kind of essential in allowing us to learn in sort of interesting ways and operate at that middle of the spectrum that we talked about at the beginning of this presentation. So with that, I just want to list here the key papers I talked about, and acknowledge all my collaborators and past advisors that were essential in making this work possible. Yeah, thank you. Open to more questions.
Yeah, I'll probably take a question here. Like, I was wondering, when you're presenting, especially the differentiable optimization part, like when you're solving nonlinear least squares, typically in SLAM or like other problems that are highly nonlinear, it seems like the initial guess has a big role to play. Like if your initial guess is somewhat off, the optimizer is probably converging it into perhaps another basin altogether.
Yeah.
In which case, the derivatives or the gradients that you get, do you have any insight on that, whether they're still relevant?
Yeah, I think so. I mean, there are two aspects to this, I think. One is just, initialization for complex nonlinear objectives is always a problem, and your performance really depends on what your initialization was. But I see this as like a good opportunity to leverage machine learning, where you don't need to learn how to plan, you just need to give a good guess, which is far less restrictive. Then you can rely on some, differentiable planning techniques like this one, and improve on sort of the rough predictions that neural networks might make. So there's a lot of work going on in amortized optimization, which is kind of like a similar idea where you're trying to make better initial guesses so that you have to spend less time optimizing, and this sort of fits in that sort of philosophy. And I guess the other thing that I would mention here is I kind of lost my train of thought. Let's just leave it at that. I think initializations can be probably learned. Yeah.
I had a kind of a related question. There's also like a line of work in SLAM related to like certifiability or trying to impose guarantees, or like I'm thinking of like work from like David Rosen and Luca Carlone and people like that who are trying to guarantee with some bounds or with some assumptions like optimality. And it would seem like in the case of planning, this is kind of even more important, right? Because like you might want to have some guarantees that you're not going to like violate some conditions or run people over with a car or whatever. Can you think can you see that kind of thing like integrating into this framework also?
We've had some initial discussions on this. I think it's a little bit hard. Nonlinear least squares is kind of a soft way of dealing with constraints. So what you actually want is constraint optimization. If you have constraints that are hard constraints, then there's no way you can violate them. So something like augmented Lagrangian or something could be possible here. It's not so much of a stretch in terms of just kind of optimization machinery, but I think it's still an open question whether it can be made differentiable. So that's something we're thinking about right now.
I have a question. Hello?
Yeah, please go ahead.
So I'm wondering how generalizable this is. So if I understand correctly, this is still assuming the location of the obstacles in the world, right? That's like the input, one of the input to your network. Is that correct?
Yes. I mean, the machinery here doesn't really prevent you from doing something different, and that's kind of what we're exploring right now. But I guess this, what we did right now stems from that inherent bias in solving planning problems where you're assuming you just kind of have the perfect knowledge of the environment to begin with. But obviously in practice, that's not true. And I think for those settings, these kind of differentiable planning techniques become even more relevant, because now you're actually relying on having perception in the loop while you plan, where you might not have perfect observation of the environment. I don't have a good answer for that. I think it's still an open question in terms of, if we have partial observations and haven't seen the scene completely, how far can just current SLAM or perception approaches take us? And is that enough for these kinds of planning methods? I think we still need to put A and B together to actually get a full working system before we can start exploring those questions.
Okay. But I guess I'm more. My question is more like, even when you have perfect observation, even when just consider the case when you know where all the obstacles is, so you can train your network. Like how big of a data set that you have to collect. That means you have to, like during training, you have to sort of have a dense samples of where obstacles might be in the world, right?
True. Yeah. I think it will vary problem to problem. I don't remember off the top of my head for the examples that we in the 2D navigation setting that I just showed how large the data set was. It wasn't prohibitively large compared to, let's say, something like an pixel to action RL technique that you would be learning from scratch. So it's definitely orders of magnitude lesser than that, but it's definitely not insignificant. It's not on the order of traditional learning from demonstration approaches where you get 5 demonstrations and you're done. I think it would be interesting to see actually if we can get towards that, but it's just hard to train neural networks with so less data. So I don't know if that's possible.
Okay, thank you.
I have a question.
I sort of have a tangential question. This is perhaps related to differentiable planning and other like differentiable whatever. Like, how do you reconcile, or like, what are your thoughts usually on how flexible these systems should be versus how much of priors should you have? Like, priors are good, but at some extent, they get, you have too much priors that you sacrifice on flexibility. And it seems like once you tend to impose a prior, it's hard to get out of it. Like if you assume that your planning problem or your optimization function is going to have a nonlinearly square structure, then that's hard to go back on. What's like your thoughts on this?
Yeah, that's a very, very good point. I think that's kind of what I hinted at the beginning of my slides. We know we want to be somewhere in the middle of the spectrum, but it's I think pretty much open at this point. Like, what is the right structure? Should the structure even remain constant? Should it evolve or be phased out as the system gets better or gets more data? Maybe it's like an online thing where you deploy the system and phase out biases for your models. But I think that's kind of the research questions I've been thinking about these days. Beyond just kind of musings, I don't have an answer for it.
Makes sense, yeah.
I have a question, and sorry if I'm a bit off base here. I'm a bit of a beginner. What level of sensory processing or motion processing would it operate at? Like, let's say you had a really dumb robot, like a rover, with a bunch of proximity sensors, and you're trying to get it to not bump into beer cans. Could you use the readings from the sensors and the speed of each motor directly, or do you have to pre-process your environment where it's all mapped out, the coordinates in the room, where the objects are, all of that?
Yeah, that's a good question. I think I tend to think more modularly. So I would say, rather than throwing these sparse raw sensor informations directly into the planner for it to handle, it would make sense to maybe have something intermediate that tries to process those observations incrementally and maybe even attempts to build some kind of a global picture, and then that's what the planner tries to leverage. It could also be something like a predictive perception module that maybe was at training time using lots of sparse sensor data, trained to predict complete environment observations. So if you saw some measurements here and there, then maybe that's what the other stuff is, and then those kind of predictions could be used for the planner. But there's a balance there, I guess, in terms of the planner still being safe by using some completely wild predictions from the perception module.
I see.
But yeah, I guess I would start there.
Okay, so more starting with a higher level representation of your environment.
Mm-hmm. I think in general, data efficiency is much more easier to attain if the intermediate perceptions are set up so that they generalize better to different domains. If it was entirely pixels to actions, then as soon as you change the environment, now you have to just basically get data for that environment again. But if the intermediate perceptions were intermediate representations were trained in a way that abstracts away some of that complexity, then even if there was a new environment, you could still reliably get the pipeline to work, I think.
Okay, thanks a lot.
Yeah, great questions, I think.
So I guess we could take one or at most two questions. Okay, so I guess that's it for the Q&A session then. But yeah, I'd like to thank Mustafa again for accepting this invite and like for the really nice talk. It's also great to see all the speakers on very different themes. We've got two more talks to go in the series. And yeah, it's great to host you. Thanks for making like this group seminar a success.
Yeah, thank you for organizing this series and for the invitation. I really enjoyed talking to everyone.
Yeah, really great. Thanks so much.
Thank you.
Thank you.
Thank you.